Hello and welcome to Communimatics. In this series of videos, I'll talk about frequency modulation from beginning till end. And in this particular video, I'll start off by defining what is frequency and what is phase. I know these are fairly simple concepts, but I will talk about how they are related and how you can derive frequency and phase of any signal. Now, I will give an analogy of velocity and distance. So let's say that you have a car, you start driving this car, and I'm going to plot the velocity against time. So I have velocity, which I denote by v, it's a function of time t, and then I have here on x-axis I have time t. Now let's say you start the car, you start off slow, you speed up a bit, you maintain your velocity, and then you slow down again, and then you stop this car. Now in general, if you have constant velocity, our velocity definition of velocity is distance divided by time. Now if I want to find the distance from this particular curve, now how will I do that? Let's say I want to find what is the distance that I've covered from time 0 till time t is equal to t naught. All right. So how much is the distance that I've covered in this point? Now I know the definition of velocity, and the relation of velocity and distance is this, but here the velocity is not constant, it's changing. So we can take the help of calculus and we can divide this whole thing into small rectangles. All right. And we assume, so this is small rectangles, and we assume that each of these rectangles, the height is constant. So the height is constant, right? And the width of each of this rectangle is, let's say, d of t, and d of t tends to 0. It's really small, right? Now what I need to do is I have to multiply my velocity of all these points, right, at any point, and then multiply by d of t and sum it up from 0 till t naught. Now this gives me distance that I've covered from 0 till time t naught. Now this is just calculus, and now assume that we want to flip this around. I want to find what is distance. All right, so I'm plotting distance as a function of time here, and for the same example that we shown above, I'm going to try to plot distance. Let's see if I get this right. So we started off slow. So if started off slow, and then we sped up. So distance was increased, and then we slow down again. So the distance was slowed down, right? We're still covering some distance, but now the pace is slow. Now you can see already that the slope of this curve, it can show you what the velocity is. It's really related to velocity. So here the velocity is low, so the slope is low. Here the velocity is high, so the slope is high. Now if I want to find the velocity from this curve, let's say at point t naught, all right, now what I have to do, if I want to find the velocity over here, now keep in mind the velocity over here is different than the velocity over here and the velocity over here. You can see it already from the graph on the top. So the velocity at each point is different. Now let's say I want to find the velocity at this particular point. Now I would call it the instantaneous velocity. I want to call it instantaneous velocity, and I'm looking at t naught, and this would be equal to the slope of this curve. So, and slope of the curve at this particular point. So here what I'm assuming is that there's a kind of a triangular shape where this is d of t and this is d of s in this small window, and I do ds by d of t, and in this particular point, which is at point t naught, this will give me the velocity, instantaneous velocity at this particular point. Now with that out of the way, let's consider an example. let's take a sinusoid cosine theta of t. Now this guy in general is it called angle. Angle can be anything. It can be just the frequency multiplied by time, and this is also called the angular frequency. It can also sometimes be written as omega. It can also be this guy plus a constant phase offset, and can it also be 2 pi ft plus a time dependent phase offset. So this is called not the phase but phase offset. So let's consider the first of these examples and draw this cosine. So we have 1 over here minus 1 over here. This is 0, this is 0, this is a function of t. So we can take certain values of t. Let's say we take t is equal to 1 over 4f, and then we take 1 over 2f, and then we take let's say 3 over 4f, right? And then we take 1 over f. So let's start with t is equal to 0, and when t is equal to 0, we know that cosine of this whole guy is 0 and the cosine of 0 is 1. If t is equal to 1 over 4f, then we are here because cosine of pi by 2 is equal to 0, and then when we plug in 1 over 2f, we get cosine of pi, which is again minus 1, so it's some point over here. And then if we plug in this one, then we get again 0 over here, and finally if we plug in 1 over f, we get back over here. Here t is equal to 1 over f. Now what is phase in this case? Well, phase is actually theta of t, the value of theta of t at different values of time. So from time t is equal to 0, phase was 0. For t is equal to 1 over 4f, it was pi by 2. And for the next one, it was pi. For the next one, it was 3 pi by 2. And finally, it was 2 pi. Now you can say something like this, that the phase is the quote-unquote distance covered by the tip of the wave. So the sinusoid starts over here and it traverses through space, or let's say through this graph, and phase would be the sort of, it's not a really distance, but phase would be this quote-unquote distance which is traveled by the tip of this signal. So here the distance traveled is 0, here the distance traveled is pi by 2, here distance traveled is 3 pi by 2, and here the distance traveled is actually pi. Now I'm using the word distance, but it's not really distance. Pi by 2 is not a function of meters or centimeters, but there's a direct analogy with distance and velocity. So if I say that my angle theta of t is equal to 2 pi f of t, where this guy is the angular frequency, you can see this angular frequency as kind of angular velocity, right? I will repeat it again. So you can see angular frequency as kind of an angular velocity. I will give you a very descriptive example after a minute. Now, the phase would be the distance. So how do you find a distance from velocity? Remember that what we tried was that instantaneous distance covered by any car would be from 0, let's say, to t naught. If you want to find the distance, this would be the distance. Now similarly, in this case, phase at time, let's say, t naught would be equal to the angular frequency, which is 2 pi f, or the angular velocity in this case, d of t from 0 till t naught. Now let's solve this for our example of t naught. Let's say our t naught, we consider t naught to be equal to 3 over 4f. So for t naught is equal to 3 over 4f, what will happen of theta of t of naught? This will be equal to 0 to 3 over 4f 2 pi f dt. And if you can solve this, you will get something like this. 2 pi f into 3 over 4f. Sorry, the f is in the denominator here. And this would give you 3 pi by 2. This is the exact value that we found over here. Similarly, I can turn this around and find a frequency from phase. So if you remember what we did with our velocity and distance, is that distance at any point, let's say from 0 to t naught, is given by 0 till t naught v of t dt, and instantaneous velocity was given by ds divided by dt at particular time, let's say t naught. So if you want to find instantaneous frequency, which is f of I, or let's say if you want to find it if you want to find your instantaneous frequency, now if you want to find our instantaneous frequency, and let's call it angular frequency, instantaneous angular frequency, it is similar equal to d by dt and theta of t at any particular time t naught, if you want. Now in this case, our frequency is constant. Right? It's a constant frequency, is f. So if we do calculate this, it will just give us d by dt 2 pi f t is equal to 2 pi f, which is, yeah, the definition of angular frequency. Here's an example. Consider you are standing in a point here, and you want to move in a circle like this. And consider that your angular velocity, because you're moving in a circle, is w. And that angular velocity can change, so it is a function of time. And how much distance will you cover at any particular time while you are moving? And I will give you one particular illustration. So here's the example. Now you're running around in this circle, and sometimes you slow down like this, and sometimes you speed up like this, and then you slow down again. All right. So your velocity, angular velocity, is changing over time. Now in any case, you're covering some certain distance. When you speed up, you cover more distance, but when you slow down, you cover smaller distances, and that distance is exemplified in the figure above. The figure above shows how much distance that you have covered while running around in the circle. If you look closely, this is just a cosine which has a frequency changing over time. The frequency sometimes speeds up and sometimes the frequency goes down. In fact, this is a frequency modulated signal. Thanks for watching. That's the end of this video, and we'll continue later on.